Okay, so I'm going to start by defining, this lecture is about half-plane intersection and applications of it. So before I even get into the applications of half-plane intersection, I need to talk about, well, a proper definition of what a half-plane is and what the intersection of half-planes represent. So first of all, let's define a half-plane, right? We have our entire plane, right, our 2D plane. And if we draw some direction vector in this plane, right, that is like infinite, well then what we can do is we can kind of maybe arbitrarily, but you'll end up doing this consistently, pick one side of this direction vector and cut everything away, right? And so the remaining side will be some half of the plane, right? Half of the infinite plane. Now you do this for one vector, and you can say, okay, we are going to cut away the counterclockwise direction, right? Arbitrarily. And that means that if I point the vector in this direction, right, perhaps a vector that's parallel, then the resulting region that I would cut away is this region. Now notice that if these two vectors are parallel, right, this region of remaining space is unbounded, right? Now for the purposes of half-plane intersection, what we're basically always going to do, right, is we want typically the resulting region that the intersection of half-planes would give us to be bounded in some way, finite, right? And specifically, what you can find is that if you were to take a bunch of half-planes, there's one of two results. Either, after cutting away all the cutaway sides of the plane, right, you'll be left with some convex polygon, right? Or you'll be left, if I say if I only did two half planes like this, right, you'll be left with some unbounded region, right? Now, what we're going to do is first of all, we're going to get rid of this unbounded region case for the rest of the discussion by saying that in any problem, right, in which case in the situation where there could be unbounded regions that you don't want, we're going to put just 4 half planes that would represent a very large bounding box. And the reason why we want this bounding box is because the result of our half-plane intersection, right, the way you would feed half-plane intersection into an algorithm is you give it your series of, direction vectors, not just direction vectors, they have a location space. You're representing your half-plane as an infinite line, right? What it's going to give you back is a series of points that represent that convex region, right, that the half-plane intersections form. And if you don't define some infinite area result, well then what happens is that this half-plane intersection resulting in this like triangular convex polygon, right, would look the same as this one, where this region is kind of unbounded. Or sometimes, depending on the implementation, you might not even get a valid result, right? So we're always going to bound our half-plane intersection. Now, I said a little bit about the fact that the result of, after we bound our half-planes, the result of some bounded half-plane intersection will always be a convex polygon, right? That is an incredibly important fact about half-plane intersection, and is what actually motivates many of the algorithms and applications. One algorithm that you can use for the implementation of how to get the intersection of half-planes is imagine some sort of incremental approach. We start with our bounding box, right? And what we can do is we can view half-plane intersection as the cutting away of this convex shape, right? So by putting this half-plane in the intersection, right, we currently have our convex shape, right? We have intersected this half-plane, so we are essentially erasing this region, and now we have a new convex shape that we can now intersect with more half-planes, right?
What is that?
So that's going to be n squared, right? N being your number of half-planes, because the number of points on this convex hole is only ever going to be O of n, right? And so to actually cut away the region, you'll have to go through all the points, right? Delete any points on the side, kind of reconnect the shared sections, right? You'll only ever intersect at 2 locations, right? And so it's going to amortize. You might have like, it will have some amortization behavior, but it will still be n squared, right? But to kind of speed this up, right? And I'm not going to go too much into the details of the algorithm because it turns out that you don't actually need to know much about it in order to successfully use it. What we can consider is that if we have our resulting polygon that represents the intersection of a bunch of half-planes, right? If we view each of these edges, each of these half-planes, we can kind of see that as we walk around this polygon, they would be in sorted order, right? And so what we can do is, if we take all of our half-planes that we were going to intersect, right, and we kind of put them, we sort them by their angle, right, which you would not use like a trig, you would do like a cross product comparison. You sort them by your angle. What happens is that if you have your current bounding box, your current half-plane intersection, your current convex shape that your half-plane intersection is producing, well then, by intersecting some new half-plane with this shape, it turns out that the kind of sections that you would get rid of, right, will be only from, like, if you consider the array, only from the front or back of this array. And so what that means is that you can store it in like a deck-like data structure and kind of pop off area that has been gotten rid of and re-intersect the points. And that will then amortize to like this portion. You will move these pointers in like only n times, but you'll need to do your n log n sorting of the half-planes by angle, right? Now I don't expect you to be like possibly able to immediately implement an n log n half-plane intersection just based off this description, right? But the important fact, right, that you might want to realize is that there can be problems where you end up kind of intersecting the same set of half-planes multiple times, right? And what I mean by that when I say the same set of half-planes is that you won't ever change their angle, but you might change their location. And what this means is that if you pre-sort your half-planes before your half-plane intersection, right, you can cut away some of the runtime of this algorithm when you have to use it multiple times.
Is the implementation of this like similar in any way to like convex hole trick with the deck?
Not it. So line container, right? Convex hole trick.
I was talking about with the deck.
They do have like they do share a lot of the same ideas. So you will see like some. similarities in the implementation, but it would be somewhat challenging to like transfer one to the other, right? And so, anyways, so that's kind of the implementation-ish of how to implement n-log-n half-plane intersection, and specifically using this idea that the majority of the runtime is just for the sorting of the half-planes. So if you were to do half-plane intersection on shifted half-planes multiple times, you don't necessarily need to resort. Now let's get into like an actual application, right? The most kind of fundamental application of half-plane intersection, right, is since we know that there is a direct duality between the intersection of half-planes and a convex region, right, or a convex polygon or convex shape, right, what we can do is we can actually flip this, right, and also view convex shapes. If you have some convex polygon, right, well, take these edges in, you know, the order that you want to take them, right? Counterclockwise, clockwise, it's kind of arbitrary because you want to just make sure that the order in which you orientate these edges is such that in your implementation of half-plane intersection, the space that gets cut away is outside the region, right? So as long as you're consistent. Does that make sense? We can take this convex polygon and we can represent it as a series of half-planes, right? And those half-planes represent the polygon, right? They're like directly correlated. And so what this means is that, well, what if we want to then find the intersection area, right? The area of two polygons that is shared between them. We want the intersecting polygon. Now, it turns out that if you intersect two convex polygons, the resulting region will always be a convex polygon. And you might find that intuitively true, but you can also like kind of hand wave and show it by the fact that if we consider any two edges between two separate polygons, right? And then we consider the four like cases of how it could be orientated, right? Then what you'll see is we either have, you're either trying to claim that this will be the convex region remaining, right, or the concave region remaining, or this will be the convex region remaining, or this will be the convex region remaining. And in any case where that region remaining would cause like a convex, a concave turn, right, it turns out that the orientation of the half planes would have to actually be cutting away that region, right? And so, you know, not a great proof, but hopefully it is intuitively true that the intersection of two convex polygons will also always be a convex polygon, right? And so what we can do is if we want this intersection area, right, we want this polygon, we turn our convex polygons into a set of half planes by taking each of the edges and drawing that half plane. And if we throw all of those half planes into half plane intersection, then the resulting polygon that you would get back, the resulting region, would be the intersection of those polygons. This generalizes to more than two, right? You don't need to if I want to intersect, say, 20 polygons, right, or 1,000 or whatever, something where the number of points and number of edges are bounded by some like number up to maybe 100,000 or 1,000,000, you can individually take all those convex polygons, turn them into their half planes, throw all of the half planes into the half plane intersection, and the result will be the region that is shared by, that is contained within all, right, not any, but all polygons, right? Because you can kind of think about it as an iterative process of intersecting two polygons, getting a new convex shape, and then for your third convex shape, or your kth convex shape, this blue one is the new one that you're intersecting with, right? So it like inductively generalizes to multiple convex polygons. So that's how you can do kind of quick and dirty convex polygon intersection quickly. Any questions about that? Cool. That is probably the most fundamental, perhaps canonical application of half-plane intersection. We're going to get a bit more abstract and talk about stars. So, you know what a star looks like in your head, right? How you would draw a star. But in computational geometry, what a star is it is any simple polygon, right, that has some region of it in which any point of this region might be a single point, right, or it could be an area. A star is any convex polygon that has some region where if you were to stand in that region, you can view the entire perimeter of the polygon, right? So if I put a blue point here, we can see that from this blue point, we can scan across and we have view of the entire perimeter, right? Now, any convex polygon will always be a star, but we can see that many is maybe an abstract word in this context, but many simple polygons may also be star-shaped. And what we call this visibility region is the polygon kernel. And so this is the kernel of the polygon, or i.e. the area that you can stand inside and view the entire perimeter. Now it turns out that we can actually easily find this kernel, or at least find/check if it exists, right, if it's not empty, and it'd be very easy to draw a shape that does not have any point that you can stand and view the whole thing, right? So it might have an empty kernel. Well, what we can do is, it turns out that for any like simple polygon, if we go through each of the sides, I should have used that polygon as an example. I'm going to redraw it. Yeah. If we go through, we can see that this is the kernel of the polygon. But what happens is that for this simple polygon, if we actually take each of its sides and we get the half-plane intersection, right, of these lines, the resulting region will be the kernel of the polygon. Now, why is this the case? Well, we can think about half-planes as kind of a visibility barrier, right? And what this means is, like, to be in the kernel of the polygon, you need to be inside the polygon, right? And well, we can redefine being inside the polygon as for every edge of the polygon, right, you need to be on the correct side, right? So for this case, you need to be, for this edge, you need to be on the correct side of this edge, right? Which is very kind of similar to what a half-plane is, right? You have the region that the half-plane cuts away and the region that it keeps. So being inside this shape is the same as being on the correct side of all these edges. And then also, what we can see is that if we have some kind of wall, right? So we can see that this point, right, can't see, like, kind of this area. Well, that not being able to see this area is actually because of the restriction of this half plane right here, right? We can see that the half plane not only determines, if I were to, let me maybe make this diagram more clear, right? We can see that this half plane restricts the visibility, right? And not only does it restrict the visibility, but it restricts the visibility when kind of combined with this half plane, right? It restricts the visibility of this region because of that, like, cutting away, right? And so it turns out that the half planes, they both act as, like, information on visibility and also information on whether or not you are inside the simple polygon. And it turns out that when you just combine it, right, that the half plane intersection of all the edges of a simple polygon, that resulting polygon will be the potentially empty convex region that represents the kernel, right? And so that is how you can use half plane intersection to find these called kernels of convex polygons. As it turns out, you just take the edges and you throw them into half plane intersection. You may also see some problems where there are points in order, and I'm not going to go too much into this because I want to keep this as a practice problem. But what I also want to illustrate the idea of is that not only does visibility exist in the context of polygons, but it exists in the context of point orderings. And so what I mean by that is that if I'm at some point A, right, and I make the claim that if I were to, like, look at these points in order, right, if I were to kind of turn in a circle, that I would see B before C, right? Well, for me to see B before C, let's say I'm saying that I'm moving, what's better for this example? Let's say I'm rotating counterclockwise, right? So I'm going in this direction, right? Well, then to see B before C, right? What you will notice is that you'd have to be in this half plane region, right? Did I get it backwards? No, I think I got it. I got it correct. But regardless of if I got it backwards, so funnily, when you implement these problems, a very common trick for a half plane intersection, just so you don't have to think about it, is put the half planes one way. If you don't pass samples, flip them, and it's probably right. I've done it many times. And we can see that if we want to kind of see B before C in this ordering, that represents a half plane or region that you can exist in, right? And so if you have many of these ordering constraints, you could perhaps see how that would generalize to half plane intersection. There may be a practice problem that uses that idea. So using half planes for visibility, for several different visibility problems, can be quite useful. What is... Okay, so any questions so far? Because I feel like I'm going quick and I still think I'm covering all I need to cover. So the third application of half plane intersection that we can get into is this idea of shrinking polygons, right? So if I want to take this convex polygon and I want to shrink it, right? One way you could do that is to just scale the polygon down, right? That is a valid way of shrinking. What we're going to consider the case is this idea of, I kind of want to go around and trim away from the polygon. And specifically, I'm going to make a very small side here, right? What I want to do is I want to imagine shifting in all these sides, right? So I shift in each of these sides by some distance, right? Now, this is not the same as like finding the center, scaling the polygon, and making sure that it's in the same center. Because if we were to shrink in all these sides, right, if I shrink in enough, what ends up happening is I would completely get rid of this side, right? This like disappears. And specifically what I'm kind of doing is I'm saying, if I were to shrink by some distance d, what I'm finding is the region inside that is at least d units away from any perimeter point, any edge, right? And so how could we do this with half-plane intersection? Consider just the very canonical problem, right, of I want to know, right, I'm inside this polygon. I want to know what is the furthest I could get away from any of these edges while staying inside the polygon. This is an open question. I'm going to give you guys a second to think about that. How would I, and don't consider we have the ability to shrink this polygon. How might you find what is the distance that you would have to, what is the furthest that you can get away from any edge of this polygon? Don't say half-plane intersection. It is half-plane intersection, but don't say half-plane intersection.
Could you binary search on this?
You could binary search,
Is it too
right?
slow?
No, it's not too slow. It's actually exactly what we want to do. What we're going to do is we're going to binary search by the amount that we can shrink this polygon until the result is like empty, right? And since it will be like a floating point binary search, you know, you'll do it as a floating point binary search, right? As in, are we finding when it becomes empty, or like the epsilon before it becomes empty is kind of irrelevant. Now, how do we shrink the polygon? Well, what we can do is, as normal, we take our convex polygon, right? We take our convex polygon, we represent it as a series of half planes, each of these edges, right? And then we want to move these edges inwards, right? Now, how do we want to move these edges? Well, we want to find this perpendicular vector from each of these edges. And what we're going to do is, since you know this edge is just represented by 2 points, right? We will, if I want to shrink the polygon by some amount d, we're going to shift these 2 points that represent our half plane in this perpendicular by a distance of d. Does that make sense? And if we do that for each edge, right, we will have a new set of half planes, right? They will like kind of, you know, intersect and have some like extra tips here that will get cut away by the half plane intersection, and we'll get our new shrunken polygon, right? Any sides that would like disappear during this process will disappear as we want them to, and what we will effectively have is the region that is, if we move each of these half planes in by d, the region that is at least d units away from any edge, right? And so now, okay, simple maybe extension, right? I give you a convex polygon. Tell me what is the largest circle that you can fit inside? You're allowed to answer. What is a circle? What does it mean to be a circle? Right? So what it means to be a circle is it means to be some distance, right, from the center point. It's probably what you think it is. It's just the same thing. It's the exact same problem, right? We are essentially taking this radius, right? You can kind of see this trick a lot, right? Where, say I have two circles, right? You can kind of do this idea of like transfer, right? Where if I want to know like where's all like the points that this smaller circle could move around in, well, I can take its radius and I can add it to the other circle, right? And that gives like the region it can go without intersection. We can do the same idea, right? And for this circle, right, I want to know what the largest circle that I can fit inside this convex polygon is. That is equivalent to saying, well, this center point of the circle can't be within like radius of an edge, or else that there would be an intersection, right? So what we need to do is to check if some circle with radius r can fit inside the polygon. We need to shrink all of the edges, or we need to move in all of the edges of this polygon by r and see if there is any region that we can put the center of the circle at, right? If the intersection of these half planes after we've moved them in is non-empty, we know we can fit a circle of radius r inside this polygon. Not only do we know we can fit it inside this polygon, we actually have the region of points that we could place the circle. Then we can binary search on this radius because it will be monotonic, because for any circle of this radius, I could, at the exact same center point, put a smaller one, right? This will be monotonic. We can binary search this and solve the problem, right? Now let's imagine an extension, right? I want you to fit two circles of, let's just say, diameter x in the polygon, right? Such that both circles have the same diameter. They have the same diameter. I want to know what the largest x could be. Just for variable names, I'll say what the largest diameter of the two circles could be, such that you could fit them both inside the polygon. This is not exactly the same, but it's very close to UCF Local's 2021 security fence, which was the last problem, maybe 2022. Security fence, which was the last problem on a local set a few years ago. Yeah, the circles can't overlap and they can't intersect with the region. And while you're thinking about that, I'm going to check to make sure the recording is still going. It is, and the whiteboard's getting very dirty. Could I draw two circles? I will try my best. I'm not a very good artist. Oh, it doesn't even intersect with the edges. I don't even think they're the same radius either. I'm not sure if this is helpful, but I hope it is. that I can visualize. I'm tempted to cut this out and actually give you a few minutes to think about this. Do you have something? No? I'll give you a hint. It involves half-plane intersection. It also involves binary search. Because I think everybody can agree that this is a monotonic function, right? If I can fit two circles of diameter d, I can definitely do d minus epsilon.
Yeah,
Okay?
I think I have something. So
Okay.
if you have the set diameter d,
Yes.
you want to check whether you can fit them.
Yes.
So I think you want to shrink until the diameter of the polygon is equal to d.
Depending on how you implement that, potentially, I'm going to slightly change your solution. And I'm going to say to check a potential answer of d, we will shrink.
Oh, yeah, sorry, shrink by d and then check if the diameter is at least.
Well, yes, we're going to, well, we're not going to shrink by d. We're going to shrink by d over 2, right? Because for some circle, its center point, the radius is how far it has to be from the endpoints. So if we're checking some region, right, we're saying, okay, I want to place the two circles, their center points, right, if they have radius, or if they have diameter d, their center points must lie inside this polygon, right? And then they also need to not intersect each other, right? And so what I need to do is I need to basically see how far away, right, I can kind of place these circles while maintaining like inside the polygon, and how far away we can place them. And this is, you can definitely fit bigger circles, right? But how far away we can place them is going to be the diameter of that polygon. So you can binary search on the answer for the diameter of the circles, right? Shrink the polygon by that amount to make sure that the circles do not intersect with your polygon, right? Because the resulting region will be anywhere where you can place the centers without intersecting your polygon, right? And then the diameter of this polygon will tell you how far away you can place these circles from each other, and that diameter needs to be at least d so that the circles don't intersect, right? And that's your binary search. And then to make sure that you don't have like an n log squared solution, right? We don't want n log squared, ideally. Maybe the n is 1,000,000. We can remember that in half-plane intersection, right, the log factor, where we can say the runtime of the algorithm is n log n on n being the number of half planes, comes from the sorting step, right? And so we don't actually have to do that sorting step each time, since the half planes in the implementation will be sorted by angle. We can actually pre-sort them, and the rest of the half-plane intersection algorithm will be linear. So we can actually do the full problem in n log n, even with our binary search, right? Which may or may not be necessary depending on the bounds of the problem. Any questions about that? I know the diameter part, might take some convincing or proof of like, if you place them at the diameters, they won't intersect and it won't intersect any other polygons. But hopefully you can wrestle that into being believable.
I think if you draw the two circles like next to each other, the closest they can be is when they're tangential, right? And so then the distance between their center points has to be.
Are you saying, like, let me try drawing it, like, let me try drawing, oh, I don't know if I can draw this this intersection well, but we can see, like, if I kind of place the circles on the diameter, well, I didn't do it right because there's space here, but I'm an artist, but hopefully that solution makes sense. If there's any questions, ask now. Yeah. Okay. So that is definitely one of, like, the most common applications of a half-plane intersection. The idea of, like, just shrinking the polygon. It gives you a new way of shrinking, right? Because before, if you wanted to shrink a polygon, it would be some scaling of the polygon. This gives you, like, a new definition of what it means to shrink a polygon. And the most easy way to wrestle with what that definition is you're finding the points that are not within some distance of the perimeter. And we see a very important line that I drew for no reason. So, we're cooking. Got two more. Now, this is a relatively obscure application, but one that you should be mindful of nonetheless, because it's fundamentally maybe different in view from the others, and maybe hard to recognize. We can consider some problems, and these are called linear programming problems. Well, they're not called linear programming problems, but they fall under the umbrella term of linear programming.
Linear problem.
Linear problem, sure. Oh, linear problem. Linear programming. And what we're going to do is we're going to solve a maximization problem. And specifically, we're going to have some set of constraints. And we can say constraint A. If we have two variables, we'll call them x1 and x2, right? We say that constraint A says that x1 plus x2 must be less than or equal to, I don't need this bounding box. Constraint A plus constraint A will say x1 plus x2 must be less than or equal to 150. We'll say constraint B, x1 for x1, so some multiple of x1 plus some multiple, which we'll say is 11, must be less than or equal to 880. And then another constraint, we'll just say x2, right, has to be less than or equal to 60. And you can tell that I'm a programmer because I've drawn all of my less than or equal with two symbols instead of one. Now, these constraints, first of all, you can view the fact that I haven't even written the x1 variable here as just a 0 multiplier on x1, right? But in general, right, I know I've given specific examples. In general, what these are is some multiple of x1 plus some multiple of x2 has to be less than or equal to some constraint, right? Now, first of all of these could be negative. And second of all, is that these inequalities can actually be greater than or equal to, right? Or greater than, or less than, right? Less than or equal to and greater than or equal to kind of lose meaning when you're talking about, floating point and decimal and epsilon and stuff like that, right? But the idea is that these can also change in direction. And what we could also do is we can view the set of possible answers, i.e. the set of possible values that I could give to x1 and x2 such that all of these constraints are met geometrically. And the reason why we can do it geometrically is because we only have two values. The reason we can easily visualize it geometrically, I should say, is because there's only two coordinates, or two values. And so specifics of the angle, right, are going to be like completely wrong. But what we can see is that if you like graph the lines, right, that these that might be a bit off, but if you take these equations, right, these linear equations, and you re-represent them in kind of line form, right? Do we all agree that, you know, you could replace these with x and y and you get some equation that you can visualize or represent as a line, right? Well, we can represent them as lines, and then also we can take these inequalities, right? And that tells us like which half-plane area to cut away, right? And then we get some bounded region. Now, what I didn't do, right, is I didn't give, you know, some additional kind of implicit constraints, right, that you would get from your bounding box or from putting in the half planes of saying that they all, like the region, the values can't be negative, right? And so then what we get as a result is, you know, I'll erase all the fluff, right? And we get some bounding box, right, of valid answers. Now, what I haven't actually done while explaining all this, right, is I've said, oh, you can have these values and they'll give you some region of possible answers, right? But like, first of all, cool. We can check if there's some possible answer, right? Because we can represent our equations as lines and specifically half planes because of the inequalities, and we can get our region, and we would actually be able to determine, hey, is there some value for x1 or x2, right, or for x1 and x2 that I can set that meet all of these inequalities, right? And the answer to that would be, is the half-plane intersection of the lines that you take when you take these inequalities and draw them as lines, right, is that region not empty? But we can actually even go a step further, and we can define some function, right, of gx1, x2, right? And what this function is it is u times x1 plus v times x2 for some values u and v, right? Basically, it is some vector u and v that we will dot product our answer with, our resulting x1 and x2 values with. And we want to maximize this value g, right? So now not only do we want to know if there's some answer, but we actually want to know the values of x1 and x2 that maximize this function g, where this function is the form of multiplying some multiple of x1 and some multiple, adding some multiple of x1 and some multiple of x2 together, right? For some specific values u and v. So u and v define the function. Well, what it turns out is that this g function we can represent as like a vector, right? And we're trying to maximize the dot product. And if we take the perpendicular line, right, for this vector, each of these perpendicular lines, as we move across, right, any point on these lines, when you take the dot product of this vector with those points, right, actually gives you the same number, the same result. And I'm not going to prove that mathematically, but you can be my guest. If we take this line and this perpendicular line, and what we're basically doing is we're getting the distance right? Kind of in that direction. Anywhere on this line that has the same distance will have the same result, right? And what that means is that if we shift this line across, we're increasing our answer. Well, all of the critical points where we stop being a valid answer, right, are going to be vertices of this polygon. And so what this actually means is that for some arbitrary function that we're trying to maximize, we only have to check the vertices of this convex shape, and one of those will be our maximal answer. This is kind of absurd, and is actually a very restricted form of kind of the general problem where, you know, there's an x1, x2, x3, right? Many variables, right? And in the general problem, you can still solve this with something called the simplex method or the simplex algorithm. And it turns out to use many of the same ideas of the answers always being vertices, but at a certain point it stops being geometrically representable and they're called pivots instead. And this simplex algorithm that solves the general form of this, its runtime is actually exponential in nature, but it's kind of only exponential on paper, and in most cases tends to have just very good results, very good runtime. But if we reduce the problem enough where we only have two variables, we can, instead of using this kind of hammer of simplex, one that we can't reliably pin down the runtime and one that, you know, is kind of painful to implement, we can actually view this as just a geometric problem and use half-plane intersection to find these potential critical points. Yes?
Maybe is simplex just exponential with respect to dimensionality, or is it also with respect to like the number of points?
So simplex, I don't actually have a good answer to that. I don't know that off the top of my head. It's possible that in 2 dimensions, the like upper bound on the runtime of simplex may be like more strictly bounded, but even in that case, simplex is a much more complicated algorithm to write than half-plane intersection, which is like 20, 30 lines. And this is like much more easy to debug and visualize. And so I would tend to, if you're in a situation where you can actually reduce your linear programming problem to only 2 dimensions or only 2 variables, to instead of like throwing simplex at it, think about it in the context of a geometric perspective, like a visualizable geometric perspective, and potentially solve with half-plane. Because it will, at the very least, probably be faster. It will, like, constant factor-wise, it is probably faster time complexity-wise as well. But I could not confirm that off the top of my head, if there's some stricter bound that you can put on simplex based off the number of dimensions. Yeah. Almost done. Is my recording still going? Looks like it. Cool. So now, this is kind of the last one, but it's also the beefiest one. We're going to actually abandon. I don't actually know how to spell this. Okay, it's with an O. I thought it was with an A for a second. We're going to abandon the idea of half-plane intersection and instead focus on this idea of something called a Voronoi diagram. And what a Voronoi diagram is is that if we have some set of points in the plane, right? There's this question of distance, and specifically, well, let me try to do this. So I'm going to do
Close enough.
it's probably something like this. It might be a little bit weird, but essentially, it's a little bit off, but essentially what we can say is the Voronoi diagram is some tessellation, right? Some kind of lattice where for each of these points, they have a bounded or potentially unbounded, which we will just put a bounding box on the whole thing, right? Bounded or unbounded region in which we can say for any location inside this region, right? If I were to draw a point inside this region, this blue point is the closest to this black point out of any of the other blue points I've drawn, right? And so what happens is that each cell, right, kind of gets a region of ownership. We call these the Voronoi cells, right? And what this region of ownership is that this is the region where, you know, every location or every point, right? But if I keep using the word point, it's going to overload it. So every location inside this region, this blue point will be the closest, right? And we want to compute this Voronoi diagram and potentially solve some problems with the Voronoi diagram. So how do we do that? Well, let's just kind of do it. Consider 2 points, right? And I just want to make the Voronoi diagram of these 2 points that happen to be having the same y, right? What we can notice, right, is if I want to move in, right, and I want to find a location that is equidistant from both points, I'm going to draw that point directly between them, halfway between them, right? And then what we can see is, like, if we shift this point upwards, right, both of the angles change by exactly the same amount, right? If we shift it downwards, both the angles change by exactly the same amount. And then we generalize this, and we notice that we can actually draw a line directly between them, right? And what this does is this line represents all of the points, right, that are exactly equidistant, right? All of the locations that are exactly equidistant between these 2 blue points. And, like, you know they're equidistant because we kind of went from the straight line distance between them, and, like, as we shifted it up, the distance function, the distance equations, like, end up having, like, exactly the same vectors, right? And so this line represents exactly the points that are equidistant, right? Well, now what happens, right, is what if we consider any point in this region? Well, now the x hasn't changed, right? But it's gotten closer to this point. The x hasn't changed. The y hasn't changed. But it's gotten closer to this point in x value and further away from this point in x value, right? And so bear with me. I'm not going to do the math. I think you can trust me. That essentially any point inside this region will be closer to this point, and it's you know, very clear when you even go past this side, right? And any point inside this region will be closer to this point, right? Well, all we now have to do, right, is say, oh, well, it doesn't actually matter that it was vertical, right? We can draw the 2 points anywhere and draw this line anywhere, right? And, you know, everything still applies, right? And so between 2 points, we now have like a region that this point owns and a region that this point owns, right? So what we're going to do actually is, instead of computing that Voronoi diagram all at once, we're going to consider a single Voronoi cell, right? Which is the kind of polygon the polygon of ownership around a specific point, right? And the way we get a specific Voronoi cell is we draw these lines, right, for every other point in the set of points, right? We draw these lines. And what these lines are is they are, if you want a name for it, the perpendicular bisector, right? Which makes sense. It's perpendicular and it bisects. Right? And so it turns out that for this given point, right, inside that we are trying to construct the Voronoi cell of, right, well, we know for each of the resulting points, we basically have a perpendicular bisector, right, which half-plane intersection we have created for any perpendicular bisector. We basically say, hey, everything on this side of the line, everything in this half plane, right, I am closer to, right? And so if we do that for every point, right, we kind of get that half plane for every point, what we've done is we've said, okay, everything that hasn't been cut away, if it's in this region, it is closer to this point than every other point, right? Like we've kind of, you know, we've taken the word intersection sort of literally, and we're anding the if statement, right? We're anding the if statement that says, hey, if you're in this region, you're closer to this point than this point. If you're in this region, you're closer to this point and this point. So we're finding the section where everything is true for all those like if statements of are you closer to this point than this other point, right? And so we get this Voronoi cell for a specific point, right? And what's interesting about this is, right, is that by getting this Voronoi cell, like that is our Voronoi diagram algorithm, right? Because we can store each of the cells. We can store each of the cells, right? And process anything where we need to process the Voronoi diagram. We can process it in whatever cell that we are actually looking at, right? Now, some properties of this Voronoi diagram. First of all, for a specific point, right, we might want to consider how many edges that its Voronoi cell could have. Well, its Voronoi cell could have n-1 edges for each of the other points, right? If you like equidistantly kind of place them correctly and maybe like I don't even know if this would even work, but right? But if you potentially got it to be perfectly equidistant, you could imagine the polygon that would like have a side for each point, right? Even after you do the half-plane intersection. But what does happen, right, is the total number of edges when you sum across all Voronoi cells does not end up being n squared in nature. It actually is bounded by 3n minus 6. Now, some of you might recognize this number, right, or this formula. And the reason why it's bounded by 3n minus 6 is we don't actually even need to kind of prove it in context of Voronoi diagrams. What we can see is that this tessellation of the Voronoi diagram is a planar graph, right? And so we can actually steal all of the proofs and properties for planar graphs to say that in the resulting Voronoi diagram, the total number of edges for each cells will be at most 3n minus 6. Like, just completely steal it from any proofs you've read about planar graphs, right? There's also another bound, and we can say the number of nodes in not nodes, vertices in the Voronoi diagram is 2n minus 5, right? And that's like harder to prove, but you could always at least bound it by like the number of edges, because how are you going to have like more nodes than edges, right? So knowing that it's exact like 2n minus 5 instead of 3n minus 6 is not really relevant, right? But what that means is that if we have some algorithm where we need to process the cells, right, in potentially with time complexity that is, scaled with the size of the number of edges in the cell, which, you could expect, right? You don't need to worry about kind of cubic, squaring behavior for your cell regions, right? Now let's actually solve a problem with Voronoi diagrams. And ironically, the easiest problem that I could find for Voronoi diagrams is a World Finals 2018 problem. And a preserve. So consider some simple polygon. Wow, I'm not very good at drawing. Consider some simple polygon that represents the panda preserve, right? And what we want to do is essentially put kind of feeding stations or security cameras or some thing. I don't quite remember the flavor text at each of the vertices of the polygons, and we are going to put these security cameras at each of the vertices of the polygons, right? And what's going to happen is that they're going to cover some circular region. Yeah, that's not a circle. In like how much they can view, right? And all of these circles will be the same size, which they're not going to be in my drawing because I can't draw, right? But what we want to know is how large of the circles, how large do we need to make all the circles such that the entire polygon is fully covered. And I don't mean the entire perimeter. I do mean also the inside area, right? And so in this problem, n was up to 2,000, right? And it had like a 10-second time limit, so it was a very generous time limit. So I'm going to cut to the chase, and we're using Voronoi diagrams. Yes? No, if you have a potential solution idea.
Like you take each cell on the Voronoi diagram and basically.
Where are you getting your cells from? The vertices? Are you saying the cell made by a vertex?
Yeah.
Okay.
And basically your goal is just to find what point in each one is furthest away from the center.
So yeah, you are exactly correct. That is the goal. But there is more to it. So we can kind of agree, right, that an equivalent problem, right, is what is a point, or what is the distance of some point inside this polygon, right, that is furthest away from any of these vertices, right? Because if we know that distance, we know the circles, that we know the radius of the circle, right? And so what we're going to do is we're going to get a set of candidate points, points that could be the answer. And specifically, if we consider, right,
Wouldn't those have to be like the vertices on the cells?
not necessarily, but most of the time. Well, most of the time is a silly phrase. Wow, I don't know how to actually draw the Voronoi cell of this. Let me see. So it's going to be like this. So if we consider some Voronoi cell, right, for this point, you are correct that if I'm trying to find, right, like the furthest point away from some sets of points, in the kind of general case, it's going to be some vertex of the Voronoi cells, right? And the reason why is because if we shift inside the cell, right, then we've gotten closer, right? If you're on the boundary, like this is all, we can already kind of say that this is the limiting cell, right? Now, technically being on the boundary makes you equidistant from this point to other points, but we'll say that this point has claimed you already if you're on this boundary when we're considering the cell, right? You get no benefit from going inside this cell, right? You have now gotten closer to this point, but this point was already the thing that you were trying to stay far away from, right? If you move outside this boundary, right, you've now moved closer to some other point, which will now be the point that claims you when you're trying to be far away from everything, right? It's going to be the point that you are now closest to, right? The point that is defining your distance,
So
right?
in case like some point on the boundary of the polygon then?
Yeah, so for a given cell, right, it's always going to be some point on the boundary. But we can,
On like the original polygon, like this, if it's not a vertex of the.
If it's not a
cell, then
vertex-
It has to be on the boundary of the polygon.
yes.
So, could you add in like the polygon size into the pathway section? Or was that too slow?
That would be very messy very quickly. Yes.
You wouldn't have to, because you could look at just like the length of each of like the segments of the blue polygon and divide it by half and have that be the crossover next. Right?
You guys are coming up with very creative solutions, and I'm going to give you the non-creative solution. For every cell, right, we want to try to find like the furthest point, right, the candidate points, which we agree that if we weren't trying to stay inside the polygon, right, well, first of all, we only want to consider the points that are inside this polygon, right? So we're only going to consider the vertices that are inside this polygon. We're going to do like an inside polygon check when we even consider this vertice. And I didn't fully explain why it would be fully vertices. We kind of agree by this point that it would be on the boundary, but you can do, you can basically make an argument that for any point on the edge, you can, shift it towards a vertex without decreasing the answer, right? Because you're essentially, if we, if we consider the point right here, you're not changing the kind of horizontal distance, but you're increasing the vertical distance, right? So you can shift it towards a vertex. And so in the problem without the polygon, the answer would always be some vertex, right? If I just gave you a set of points and I want you to know, hey, what's the furthest away that you can get, while, staying in some region, otherwise the answer is just go off to infinity, right? It's going to be some vertex of your Voronoi cells, right? First case you have to consider is don't consider vertices that are outside the polygon, right? And then the second thing is, you guys are talking about it has to intersect, right? It has to be on the boundary, right? So let's just do it, right? For this cell, intersect each of the lines with the kind of each of the edges, right? And any of the lines that, any of the points that intersect, any of the points produced by an intersection, also check those, right? For their distance from this point, right? And the reason why is because what we can do is we can basically make the same argument for shifting to a vertex to saying, well, okay, I can't like go all the way to the other vertex, right? That's probably like a better answer, but I can shift up as much as I can, right? And so that's why what you do is for each cell also intersect all the lines of our actual playground or pen preserve with each of the lines, each of the edges of the cells in the Voronoi diagram, right, for a given cell. And that gives you all of your candidates that you can check their distance to their kind of representative point of their cell and get your potential answer. So n was 2000, right? We already talked about before that like the actual number of edges in each cell in a Voronoi cell will be bounded by like 3n, right? So this ends up giving you like an n squared log n solution. I have one more kind of cool Voronoi problem if anybody has any questions about this. This is something that you guys should probably implement. Knowing the solution, of course, like takes some of the fun out of it, but I still think it's worth the practice of making a Voronoi diagram and using it. One last cool like application of Voronoi diagrams, right, is that consider the problem of I'm giving you a bunch of circles, right? And as a kindness, and trust me, it is a kindness, all of these circles will have the exact same radius, right? We'll say their unit radius. And what I want you to do is I want you to find the, so for now, I'll say 2,000 circles, right? And I want you to find the unioned area, i.e. any spot that's inside any of the circles, not counting the overlapping regions twice, right? No double counting. This is a very, very painful problem, right? So you can do some like sweep line shenanigans and some like radial sweep shenanigans and like any other solution I could think of, I would only refer to as shenanigans because it would suck a lot. But if all of the circles are the same radius, we can actually use Voronoi diagrams to solve this problem a lot less painfully. Does anyone want to try to take a crack at it before I get into a solution? Oh, that circle's too big.
Like, I mean, like presumably if you get like the Voronoi cell for some point, I mean, if you intersect the circle with the cell, like you can find what area that would cover, and like it would like and like the same area would never get counted twice because like each intersection is like divided up.
Yeah, basically, exactly. First of all, kind of cheating, right? But we have to assume we know how to solve the problem of find the intersection area of a single circle and a single polygon, right? You can do some like annoying calculus, or you can throw Cactal at it, which has this problem. So we are going to assume we know how to solve this problem, right? Which, you know, maybe is a meaty assumption to make, given that that is not a easy subproblem to solve, but it is one that is relatively short code and one that exists in most team reference documents, right? So then all we have to do is for this point, right? If we construct its Voronoi cell, which we get from all these other points, we can basically now claim, this point will claim any portion of the circle that is inside its cell, right? And that will stop the double counting. And that's how you would solve that problem using Voronoi cells, is it stops you from like over counting the overlap. And then what happens if I then up the bounds to 100,000, right? The computing the Voronoi diagram of some set of points is like n squared log, right? N, so that's probably not good. One thing that I haven't mentioned is that there is a kind of other geometric, I'm gonna probably spell this wrong. Another geometric item, I'll call it, called the Delaunay triangulation, which this has been kind of a running bit, or maybe not for you guys, but there's a running bit that the use of the Delaunay triangulation is that the MST of a set of Euclidean points lies on the Delaunay triangulation. Now, I'm not going to get into the exact kind of definitions of what a Delaunay triangulation is, but what you'll actually find is that the Delaunay triangulation is sort of the dual of the Voronoi diagram, and what you can actually do to construct a n log n solution to constructing a Voronoi diagram without actually using the specific algorithms like Fortune's algorithm or something like that else that are like very annoying sweep lines is take the Delaunay triangulation of your set of points, and when you are trying to construct a specific cell, right, when you're grabbing the half planes, instead of making a half plane for every perpendicular bisector of this point and every other point, what you're going to do is the Delaunay triangulation will be some O of n sized set of edges, and you will actually only intersect using the half planes that you create by taking the edge from this point, the edge that exists in the Delaunay triangulation between this point and your other candidates, right? And that would make more sense if you actually look at like what the Delaunay triangulation gives you. But what that basically means is that you don't actually need any specific hack pack for n log n Voronoi. You just have to go through the pain and misery of writing half plane intersection and n log n Delaunay triangulation, which both exist in the majority of team reference documents at UCF. Yeah, I think that's it. Any questions before I end the recording? Cool.